Cool. So let's try to close this up, because I think we're quite deep into this already, and I think that things start to become clear, at least for me, more and more, especially when it comes to this. I kind of realized right now, as I was starting the video, that of course that is a universal way of implementing a model, and it's pretty smart, because at the end of the day, with the rotations on X and Z, you can implement anything, because you can also implement a rotation on the Y axis, right? It's just nothing else than an RX and then an RZ. Um, and the RZZ isn't, I think it's just a control rotation. And, what here it says is that the, uh, basically, this allows for entangling two qubits. So that kind of, the concept here is with using this layering concept, you're basically allowing to construct any random gate, and also to create entanglement. And so that is actually pretty neat. That is actually a pretty neat model, and I think I'm going to definitely put that into one of my intuition intuition videos, because then by playing with those theta angles, then you can just, you can help it learn, implement any type of gate. So that's pretty cool. That's pretty cool, honestly. So that's really what it's doing. And so this is happening inside of each of these layers. So this is point number one. This is clear, exactly. And what else we are missing to finish this up? So we're missing to understand this this splitting in here, right? So um, how is this really implemented? How is the gradient of all that calculated? I saw here there's something like should be fairly simple. Blah blah blah. Where was that? So here it says that with this way of parameterizing, since the generators of those gates are all simple Pauli operators, it is easy to implement the conditional. Okay, let's try to figure this out. What's the conditional H's with C naughts, C phases, and CZZs, where the ZZs are between nearest neighbors qubits. So other types of ansatz may be used depending on the context. So this is another, of course, this is a list of other possible ways to implement those models. But basically what this is saying is that, so this is what keeps me now a bit, it's like, this H, like, because I don't understand that generalization here. Does this mean that we have to implement for each? Does this mean, what the heck is that Hamiltonian here, and how can you decompose it into this? So but it's not fully clear to me still what this does, really. I understand the model inside. I understand the models inside, but I don't understand the gradient. I don't fully grasp this. Maybe I should just go back. Here, right? And why do you want to even minimize that? This is what's Assuming each element is generated by a Hamiltonian, an individual gate has the form. Mhm. Is used to signify the composition of a unitary transformation is elementary parameterized gates. Yeah, yeah. The derivative of gate J with respect to parameter theta is given by these. Hmm. Gradients. Using the chain rule, we find that. So this is where the magic happens. This is where I say you need to decompose that. Because of the derivative. Okay. That's where this Hamiltonian thing comes down from the exponential, I guess. Try to think a bit out loud, but like, so the reason I have sort of a conceptual gap in like why is the the gradient useful and why is that helpful? Mm. We show the general structure of quantum gradients and the structure of quantum Hessians is shown in B. Commutator. At this point, is convenient to introduce some canonical quantum gates. The gradient of parameters from the Z grad expectation value of an ancillary qubit such that this and that. Mm. Hessian is the gradient. We show that the Hessian can be measured in figure 5 such the output. The operator P section response is the operator when computing gradients. The parameterized discriminator D and G can be decomposed into respectively ND and NG gates such that grad it follows that all elements is a discriminator. So can be evaluated for each label. And okay, so let me take a look at this more in detail. So it follows that all elements can be evaluated for each label and sources R and G by the quantum circuit figure 6. Yeah, let's see, that's here exactly. We also have the expectation value of each criterion is evaluated from ensemble averaging. It may also be possible to use Bayesian methods to update parameters after single shot measurements. yeah, basically what it's saying is you just have to run that through many times to get the gradient. We show quantum circuit used to measure gradient of the discriminator with real data using XG. In figure 16a, so the XG is the identity. It says here. Generated data. Shouldn't be. And still I'm missing, what I'm missing in this paper is then what is the what is this gradient stuff? What is this damn gradient stuff? How could I figure this out? Need some help. How could I figure this out at an intuition level? Controlled Hamiltonian. Because it seems to me this Hamiltonian in here is just added extra, right? It just added extra to this to this here, right? Um, uh, and so basically what this is saying is there's like, let's assume let's add a Hamiltonian thing here. So let's call it H, right? And again, I'm not gonna. I don't know if I shouldn't call it H, because it's the Hadamard gate. So I'm gonna call it Hamiltonian. So this Hamiltonian thing here, which takes in two parameters in this case, right? Q1. It's something, I'm trying to reverse engineer this. It's something that you put somewhere in here, let's say in the middle, and it has an actual control. So let's make it like it has a control. So exactly. So, and this is the control bit. And so this means that that's why you're adding, you're getting that into superposition. So it seems like, you're gonna do that. You're gonna do that many times. Okay. You're gonna do that many times, and so sometimes you're gonna apply this Hamiltonian, sometimes you're not gonna apply this Hamiltonian. Mhm. Then you do the control Z, which I don't really also understand why completely. And this gate W, which it's making me nuts because I don't know where this is used and why is this even used at all. Where is this W used? Even in their maths, I cannot find it. How do you implement that Hamiltonian? It says here, it is easy to implement the conditional Hamiltonians with C naughts, C phases, CZZs. But it's just, bam. Mm. Since the generators of those gates are all simple Pauli operators, maybe what is Hamiltonian of a Pauli operator? Hamiltonian using written. Okay. Maybe that's the answer for two-level system. Mm-hmm. Two electrons. Terms of the respective Pauli spin matrices. Because maybe what this means is that the that this has to be applied for each of those things. For each of those gates, maybe. For each of these, you need to have a Hamiltonian, a controlled Hamiltonian afterwards. Could this be? It'll be pretty messy though. Because I don't know if that's what the notation is implying here. Solution your homework. No. Mm-hmm. Sancho press a card observe. So I'm missing that piece of knowledge. It feels like. What is the so that it's not about the really getting it completely polished and done, but it's what bothers me is the sentence that it says that it is easy to implement the conditional Hamiltonians with C naughts, C phases, and CZZs. So what are these Hamiltonians? Assuming each element is generated by a Hamiltonian. What the hell is a Hamiltonian? What is the Hamiltonian of a gate operator or whatever? Let's see, maybe this helps us. Looking the foremost. Blah. Look, so the C naught gate is its own Hamiltonian. So it seems like gates have Hamiltonians. And so here it says And so here it says that it is to implement the conditional. It's all simple Pauli operators. I mean, they are not simple Pauli operators, are they? Maybe they are in the sense that they're just rotations, exactly. For any, okay. So if I understand the question you're asking is how do we define? Exactly. Well, there are many Hamiltonians you can find that will do the job. I'll start with the easy time independent case. Given an evolution under H implements U after some time, and H has no time dependence, must be true that the eigenvectors phase also blah. Mm-hmm, mm-hmm, mm-hmm. So the procedure to calculate H from U is to diagonalize U. This is one of those topics that I'll definitely put on my list for further investigation, because I don't. This is beyond this is beyond my knowledge right now. I've gone. I feel I've gone a little bit too far. And then understanding what the Hamiltonian is and why those gradients really, why does this work at all? So I think I'm gonna make a, I think I'm gonna make a separate video independent from this one on quantum gradients, because I think that is definitely an interesting concept for quantum artificial intelligence and quantum machine learning. But I have to admit that it's currently way beyond my knowledge, and hmm. Hate that. Da, da, da. Try to see if I could figure this one out anyhow. What's the? I'm missing a clue. It's like I'm missing. So I'm guessing. I'm having an intuition that this is sort of, you need to implement the conditional Hamiltonians of these ones, right? And so you need to do these per each. That's what I'm. That's my guess. What a Hamilton. What the Hamiltonian of the gate is. I really don't know. And how that all plays together. So this is still another, this W is still another big question mark. Mm-mm. But I'm definitely going to come back to this. I have to come back to this. So, okay. Well, we just to close this up for now. So, what we have here is we have an understanding of what each of the models does and why this type of implementation works well. And it's just, I think this is it's a pretty nice pretty nice concept. So you've got all these generic just using rotations, parameterized rotations, and then you try to basically change and adapt that angle, that those 42 different parameters, and then until you get what you want. What I'm missing, and I'm going to put that aside for a while, is the concept of the gradient. So what I'm saving this, and I'm not giving up. I'm definitely not giving up on this. Not giving up on this one. I have a clue where this is going. What I'm saying, which is that you probably have or need a Hamiltonian of each of those things, but that's a pretty tough thing to build, right? But you need a Hamiltonian of each of those, really, maybe something like that, and then that's supposed to give you the gradient, which is what you're supposed to minimize. So let me sleep on this. Let me sleep on this, and let me sleep on this, and let's see if we can figure this out.